Today in class we discussed pH, and pH is potential hydrogen. And when we're talking about the potential hydrogen, specifically we're looking for the hydrogen ion. And remember, hydrogen ion is nothing but a bare naked proton. And so it's got a very, very positive charge, so you're not going to see hydrogen ions floating around in solution unattached. So when we talk about something that's acidic, if we have hydrogen ions in a solution with water, water's going to scoop up that hydrogen ion and form something called a hydronium ion. And so it's hydronium ion because it has that extra hydrogen and so it has a charge. So pH is a measurement of hydronium ions. How many do you have in solution? It's based on a scale of 1 to 14. And if you've got a lot of hydronium ions or hydrogen ions in solution, we're going to say you're acidic and you have a low pH value. So how can something high in concentration have a low value? It's because pH is actually defined as the negative log of the concentration of hydrogen ions. So if we looked at something that had a concentration of hydrogen ions of 1 times 10 to the negative 7th, if we take the negative log of this value, our answer is going to be 7. So what you could do is pay attention to the exponent, bring it down, get rid of the sign, and that's going to tell you what your pH value is. So if you got a lot of hydroxide ions in solution, then you're going to have a high pH. So your pH will be high because your value of hydrogen ions is very, very low. So if we've got a solution that's got equal numbers of hydrogen and hydroxide ions, our pH is going to be neutral. So how does that happen? Remember, if we've got hydrogen plus hydroxide, we end up with hydrogen hydroxide, also known as H2O. So remember, water can act as both an acid and a base. And if we call it hydrogen hydroxide, here's our acidic part, here's our basic part. And when you put an acid with a base together, you get something that's neutral. We don't need to see that. So neutralization occurs when an acid is combined with a base. And when we add the acid to the base, the hydrogen ions hook up with the hydroxide ions and form water, and then the other two ions in solution will form a salt. So this is going to be a double replacement reaction. So the example I've given here is sodium hydroxide plus hydrochloric acid reacts to form water and sodium chloride, which is table salt. It's not always going to be sodium chloride. There's many, many different types of salts that may not be familiar to you, but what we're looking for is that metal-non-metal combination.
Hi.
So here's some examples we did in class. I asked you to write a balanced formula for the following neutralization reactions, and the first one was nitric acid and cesium hydroxide. So we had to give a little acid review on how to write and name acids. So we said an acid was something that had hydrogen in the front. And there were two types of acids. We could have binary, which means it was hydrogen plus a nonmetal. Or you could have an oxy, which is hydrogen plus a polyatomic ion. So if it's binary, just hydrogen and some nonmetal, we're going to name it hydro, whatever that nonmetal is, ic acid. If it's an oxyacid, you see a polyatomic ion, we're not going to have a prefix. You will not say hydro. We're going to name it for the ending of the polyatomic ion. If it ends in 8, we change it to an ic acid. If it ends in ite, we change it to an us acid. Okay, remember that? So here we have nitric acid. There's no hydro, so I know this has to be a polyatomic ion. It ends in ic, so it must come from nitrate. So we look up the formula for nitrate on your polyatomic ion sheet, and we see it has a -1 charge. Now, since it's an acid, the hydrogen has to be in the first position. So I'm going to put a hydrogen here. Check the charge here. Hydrogen's a +1, nitrate's a -1, so it's a 1-to-1 ratio. Okay, for the base, ends in hydroxide. That's how we know it's a base. So the hydroxide polyatomic ion looks like this, and it's a -1. Cesium's in group 1, and it has a +1 charge. So this one is written correctly as well, so it's 1-to-1. Now remember, being a double replacement reaction, we're going to take the positive ions off, and we're going to swap their partners. So hydrogen is going to end up with hydroxide. Cesium is going to end up with the nitrate. So let's look at our products. We have hydrogen hydroxide, also known as water, and cesium nitrate. This is our salt. Metal, non-metal, it's going to be a salt. Now, this is already correctly balanced since we didn't have to change the subscripts when we were writing our product, so this is a balanced equation. The next one, hydrobromic acid. So it starts with hydro, which means it's binary. So it's HBr, straight off the periodic table. Hydrogen's +1, bromine's -1, so that balances out. Calcium hydroxide. Calcium you know is Ca. Hydroxide is OH. Check the charges. This is a -1. Calcium's a +2. So we need 2 hydroxide ions to balance that 1 calcium ion. So I'm going to put this in parentheses. Now we're going to do the double replacement. Hydrogen's in the first position, it's positive. We're going to swap its partner with a calcium. So we're going to end up with hydrogen hydroxide, which we know is water, and calcium bromide, which is our salt. Go back and check your oxidation numbers. Remember, calcium's a +2, bromine's a -1, so it's CaBr2. Then you need to go through and balance that. The next one is sulfuric acid. There's no hydro in the beginning, so it's got to be a polyatomic ion. It's an ic acid, so it came from 8. So we find the sulfate ion on your periodic table is SO4. I'm sorry, on your polyatomic ion sheet. And it has a -2 charge to it. It's an acid, so we have to put hydrogen in the first place. Each hydrogen's a +1, so I'm going to need 2 of those to balance it. So there's sulfuric acid. Potassium we know is written this way. Hydroxide is OH. This is a +1. This is a -1. Now we're going to do the double replacement. Swap the 2 positives. So we end up with hydrogen hydroxide, which is water, and potassium sulfate. So remember, potassium's a +1, sulfate's a -2, so we're going to need 2 potassiums to balance that sulfate. You can balance the rest of the equation. Acetic acid. Here's another ic acid. Since there's no hydro, I know I'm not going to find it on the periodic table. So I'm going to go look on the periodic table for acetate. So acetate is C2H3O2. It's got a -1 charge, so we have to put a hydrogen in the first position. Ammonium hydroxide. Ammonium is NH4. It's got a +1 charge, and hydroxide's OH-. So those are all written correctly. We're going to do the double replacement reaction. Hydrogen is going to swap places with ammonium. So we're going to end up with hydrogen hydroxide, which is water, and ammonium acetate. +1, -1. Everybody's balanced there. Phosphoric acid, remember there's no hydro, so this has got to be a polyatomic ion. It came from 8, and here's phosphate. Has a 3- charge. We have to add enough hydrogens to balance that out, so we need 3 of them. Sodium hydroxide is NaOH. Do the double replacement. Hydrogen's going to swap with sodium, and we're going to end up with hydrogen hydroxide, which is water, and sodium phosphate. Remember, phosphate's a -3, sodium's a +1, so we're going to need 3 sodiums to balance that out. Now, you have to balance the equations left to right. I helped you with the formula writing. And then you might need to do some research on the last ones here. Which of those acids were, which of those acids were strong? And remember, strong acids are acids that completely dissociate in solution. And which of those bases are strong? So you'd expect the base to do the same thing.